light of time, I'm coming to the next presentations. So we shall now focus on the Euclidean point spaces. So what does it mean? So simply what we want to see is we again will move in something like a plane, but this time we want to see the distances as well. So not only the affine properties, but also we shall be able to work with distance of 2 points, distance of 2 subspaces, angles between subspaces, etc. So that's a crucial difference. So you have one more structure there, the distances. So whenever I have got 2 points, so I've got the vector between them, and I want to know how big the vector is. And what does it mean? I simply want that the difference space, the vector space modeling the affine space, will be equipped with a scalar product. So the standard Euclidean space, so the standard one is, yes, I didn't say that it's this, as just the Rn as we did with the standard affine space, but equipped with the standard, why doesn't it work? It's the standard scalar product, right? And then it's that simple as I indicated already. For every 2 points I know the distance of them because it's the norm of the vector, and we shall write in the different way with the row. And then of course a abstract Euclidean space E of dimension n is just an abstract affine space with different spaces, a real n-dimensional vectors, Euclidean space. So that's it. And now of course the points have got the distances, and the distances have got some properties, and the properties are that it's symmetric. We can recognize by the distance whether the points coincide, so 0 is available only for a couple of equal points, and there is this triangular inequality, the most important part. And in each Cartesian coordinate system, so remember, so if we just say that we have got some 0 here and 2 vectors which are perpendicular in the sense of the scalar product, then the distance is written down in terms of coordinates, and it's just what we know as the doesn't operate as one wants, as the Cartesian distance, right? So you look at the individual coordinates, sum the squares of the differences, and then you take a square root to get a norm. So without that it would be the square of the distance. And now it's not difficult to imagine if we move to 3-dimensional thing to be able to draw a little bit more. So in 3-dimensional things, so we shall have something like 3 dimensions, and imagine then there will be a plane there like this. So I will just draw a piece of plane, and then there will be a point somewhere here, and the distance from of the point to the plane will be given by the perpendicular, so the orthogonal projection, right? So this is A, here will be some A dash, and of course the distance from the plane is exactly the length of the orthogonal component. And how do we get it? So we can take any point B here, take this vector and project it orthogonally into the orthogonal complement of the difference space of the plane, right? And that's exactly what's described in this 5 and 6. So in the 5 it's just for the point, but in n dimensions, and with 6 is then for arbitrary 2 spaces. And again you do absolutely the same. You take the different spaces of those, you take the orthogonal complement of them, you take any 2 points in the two spaces, and you project the difference of them, so the vector throwing the first one into the second one, we project it to the orthogonal complement, and that's it. So it's very straightforward and exactly what you would expect. Right, so what are then the standard tasks to do, right? So like we did with the affine spaces, so you have to find the distance of a point from a space or distance of two subspaces. We talked about it already. You can be asked to construct a straight line Q through a given point which forms a given angle with some line. So that is in plane, right? So in plane you would imagine you have a point and you want to construct a line which cuts a given angle with another line. In 3D you can do the same with line and some plane, etc. You can determine distance in E3 between two lines, right? So that's again something we can imagine very easily. I will draw the picture. So in R3 you would have two lines, one line, another line, and what are we doing? We simply take 2 points. We imagine that the lines would be meeting each other and then they will span a plane, right? But we can imagine this in an abstract way. So we take the direction of the first line, the direction of the second line, we take these two vectors in the different space, they will span a two-dimensional subspace, and we take the orthogonal complement and we project orthogonally this connection between 2 points into the orthogonal complement, and that gives us a vector whose length is the difference of the two lines, right? So that's exactly this leads already to this fifth task, because this means that we can, like in the affine space, we could look for any crossbar in R3 which joins two lines, and this is given either by its difference space, so the direction of the line, or requesting that it goes through a given point. Whereas here we can find the shortest crossbar, and that's again just constructed like here, so it's very, very easy. Right, and we are coming to the angles. So the angles are the first sort of struggle we meet here, because it's not that easy to imagine what an angle of a, say, two subspaces would be, where the subspaces either have an intersection or don't, right? So if the two subspaces are one-dimensional, like the line in E3, then it's easy, because then we simply take the two directions of the vectors, look in the Euclidean space, and compute what the angle would be there. It's in a plane, right? And that's something we did already. But if it's, say, two planes like this, so imagine we would have a plane, another plane in R3. So what is an angle of those two? So definitely it wouldn't be just 0, because it's meeting, right? So we first have to restrict somehow, and what we do is we take the orthogonal complement of the intersection and cut it with it. So what we get is something like this, and this will be the angle then, right? And this has to be formalized. But let's talk about the angle itself, right? So if you have two vectors in the difference space, the Euclidean one, so what is an angle there? So we have to imagine that actually talking about an angle of two vectors, it's always a two-dimensional problem, right? So we have only two vectors. The two vectors span a two-dimensional subspace, and we already know how it was done for two-dimensional subspaces, so it's here. So we have two vectors, and we say that the cosine of them is given by the scalar product of the normalized vectors, right? So what we do is we take the two vectors, we first cut them to be of unit length, and then we look at the scalar product. And if the scalar product is 0, then it means it's perpendicular. That corresponds that the cosine is 0. If it's collinear, so just the same two vectors in the normalized form, then the cosine will be 0. No. The cosine will be 1 then, right? Because it will be just the norm of u, and u would be twice the same vector, and u would be the unit 1, right? So that's how we get it. And this works, of course, for any dimension then. So that's easy, and we can see immediately that whatever we know from the geometry of the plane is true for all the angles. So for example, we have the cosine theorem. Like here, that works with any dimension. Doesn't matter whether it's a million of components in our vectors or whether it's just 2. The same formula holds. And we also have the standard formula, which is called the law of direction cosines, right? So if you have n-dimensional space like 3-dimensional, so you take the orthogonal basis and you look at the angles to the individual vector of the vector to the individual elements in the basis. So that's this. You look at the cosines, and the sum of square of such cosines is always 1. So that's easy going. It's just from here, right? So this is all okay, but now what about the subspaces? So if we deal with subspaces, it gets a bit more fancy or ugly or whatever you would call it. So the simplest situation is if we have got 2 one-dimensional subspaces, then starting with the general idea that the angle between 2 subspaces is given by the angle of the 2 different spaces of those subspaces in the Euclidean space, we simply restrict ourselves and work only in the vector spaces, right? So it's Euclidean vector spaces now, and that will be transferred to the case of Euclidean spaces of the affine type, right? So for 2 one-dimensional vectors, we simply take their generators and we look at their angle, and notice that we have got this absolute value there. And why is the absolute value there? Because if we are dealing with something like this, we always want to take the smaller of the 2 vectors, not the bigger one. And this is taken care of by putting the absolute value of the scalar product, because this makes the number always non-negative, right? And this corresponds to having the cosine in the area from 0 to pi half, right? So that's the one-dimensional case. Now, if both of the vector spaces have positive dimensions, so you have just 2 subspaces, but their intersection is just 0, so they are independent, right? So there is no vector in the intersection but 0. So then the angle is defined as the minimum of the angles, which is achieved by taking couples of vectors, right? So it's again in the number 1, it will be exactly this, because you can take a vector here and a vector here, right? And this angle will not be the minimum, because the right minimum will be if you take the vector here, right? So and that there it's just given by the absolute value. But here, if we have got higher dimensional case, like in R3, it would be you have a plane and you have a line like this. Then of course you have many vectors there, right? So you can just take something like this, but the right one will be this one, the smallest one. And the claim is that such a minimum always exists, and we will see very soon how to compute it. That's easy. Now, if one of them is, well, empty is wrong, should be trivial, because subspaces can't be empty, it's always having at least 0 there. But if we have inclusion, then we simply claim that the angle is 0, and then the most tricky one is the fourth one. That's what I drew here with the truss shaped, say, couple of planes, and taking the perpendicular, the orthogonal complement to the intersection. It's exactly what's written here, right? So what we take is we take the U1 intersected with the complement of the intersection of those, and U2 intersected with the complement of the intersection of those, and this brings us already to the case 2. So this is about the angle. Now how to compute the angle. Also, so the first lemma says how it works if we happen to be in a situation like here with the plane, so this one, right? So clearly what we can do is we take a vector here and we project it orthogonally to the right projection, which is this one, and the angle corresponds to the fact how much is the length of the original vector shrinked once we project. So if the line would be in the plane, it doesn't shrink at all. If it was perpendicular, the vector completely disappears. And this is exactly this. The ratio, how much it shrinks, is the cosine. And that's because the cosine is just given by that, right? So that's this divided by this is cosine of the angle, right? We make the right angle here, and this is just how cosine is defined. So that's clear, and of course now we have to prove that it's really the expected formula, this one, and that it is the minimum in the sense of the other, and it's very easy, so you can read through. And now the most difficult problem comes. So everything in the rest is shrinked now to the case that we have got two arbitrary subspaces with 0 intersection. So that's our general situation now, because everything is boiled down to that. So what shall we do in such a case? So imagine we have got something like, so in higher dimensional space we would have two subspaces, one of them and the other one would be like this, and imagine, so I can't draw it in R4, but imagine it's two planes in R4, or we can also view it then in this case, right? And what we are doing is we simply take a map which is the orthogonal projection of one of the planes to the other plane, right? So imagine we would be silly, and in this very case where we have line and plane in R3, we would start with projecting of the plane into the line. So that would be the phi, right? So of course this would map this vector into something like this, and then the next projection would just map it down to this, right? And how do we recognize whether this was the right thing giving us the minimum? So we could take the orthogonal projection back, so that would be some psi, right? So first I take the first plane, so that's the U1, here is the U2, and I orthogonally project U1 into U2, like I did, the plane into the line, and then I go back with the orthogonal projection by psi, which projects u2 into u1. And how do I recognize this? Well, it's coming back to our favorite object, the eigenvectors and eigenvalues, right? Because what shall I do? So I first shrink the vector with some ratio, then I shrink it again, projecting down, and if it was an eigenvector, then it might be the right thing, and then shrinking twice will tell me how actually the angle is. If it was higher dimensional, then this case where it's just a line, so it's already one of the eigenvectors possible. But here in the generic situation, there will be many eigenvectors, right? Maybe there could be none. We have to verify there will be some at least, but we shall see there will. And then of course we want to get the eigenvector where the cosine will be the biggest one, because biggest cosine means we are closest to 0, right? So that will be the minimum from the definition. So let's have a look what's happening. So how do we write down the orthogonal projection of u1 into u2? That's extremely easy, because we simply take the scalar products of the first element of the base, this E1, with all the bases from the other one, and that gives you the orthogonal projection value. So this is the right vector. So the first element of the base is mapped to this column. And the same with the second up to the case one, right? So we have got this matrix, and this very matrix A corresponds to our map phi here. Right, and how does the psi look like? Well, that's the same thing, except we take the E dash elements from the base and we take the scalar products with the original base from the U1, the E's. Right? And looking at the matrices, we see that I mean, they are different only in the order. What's the dashed ones, what the not dashed ones. But of course, also here we have got L lines, because it's the number of the elements in the base of the target of phi. Whereas here we have got only K, well not only, but K, which is the number of basis elements in the U1, the target of psi. So the things are the same up to the transposition. So we see that B is actually the transpose of A, but then psi composed with phi, which is what I suggested to do. What I suggested to do here is nothing but taking the product of the two matrices, AT after A. And so we see that psi is the adjoint map to phi, and we have simply phi star equals phi star, and we know that phi star after phi, it's a positive semi-definite matrix. Positive semi-definite matrices have got, first of all, as many eigenvectors independent as the dimension is, and second, all the eigenvalues are real and they are non-negative. So we simply take the biggest of the eigenvalues, and we easily prove the theorem. Well, easily, so we have shown that it's really then giving us the minimum, which takes some effort, but not much. But the theorem says that the square of the cosine is given as the largest eigenvalue of the map, of the mapping. So you see, I mean, that definitely should be one of many opportunities for what we call the wow moment, right? So we have built already enough tools to be able to settle this kind of things, like what's the angle of two subspaces, by simply finding the right positive semi-definite matrix, finding the biggest eigenvalue there, and then finally knowing that this gives us square of the cosine. And we know that the cosine of alpha must be between 0 and 1, which corresponds to the angle between 0 and pi 2. So that's it for this presentation, which was a little bit long anyhow. So thanks for your attention.